So, and the next topic is octal to binary conversion. So, already we know octal number system. In this octal number system, that is base r equals to 8. And the possible number of digits are 0, 1, 2, 3, 4, 5, 6, 7. Okay. This is your minimum value, and this one is your r minus 1, that is 8 minus 1, and the maximum value. So already you know what is binary. So binary means base 2 system, and that number system having only two bits, that is 0 and 1. So these are the octal digits 0 to 7, and for this octal digits we need to write binary equivalent representations. So binary means r equals to 2. Okay, the possible number of digits are 0 and 1, so we can call it as a bit, right? So for binary case, so we can call it as bits, and remaining all other number system we can call it as digits, right? So this binary number system having two bits, that is 0 as well as 1. For these all octal digits, you need to represent its equivalent binary representations. For example, in the 0 case, I will take 0. For 0 case, I am writing 0. And one thing you need to observe here. So for octal number system, that means base r equals to 8 system. So possible number of digits are 0, 1, 2, 3, 4, 5, 6, 7, right? And when comes to r equals to 10, otherwise base 10 system, that is decimal number system, the possible number of digits are 0, 1, 2, 3, 4, 5, 6, 7, and 8 and 9. Okay, these total 10 digits, and here total 8 digits, right? So once you observe here, so from 0 to 7, okay, from 0 to 7, even decimal also having 0 to 7, right? That means what? So in decimal, whatever the values possible from 0 to 7, same values are occurred in octal number system also, 0 to 7. That means the values are same up to 0 to 7 in decimal as well as octal. When comes to here, so this is 0 to 7, 0 is the minimum and 7 is the maximum value. For example, if you take 8, so this 8 value, so if you want to represent this 8 value in terms of octal number system, 8 is what? Decimal here, right? So this decimal you need to convert it into octal form. Then what you have to do? Just you can take 8, okay, that is decimal number, okay. So now you can divide with base 8 system, right? 8 ones are, okay. That means what? A decimal to octal conversion, decimal to any other base r conversion, that is depends on successive division as well as successive multiplication. Here we have only integer value. So in decimal you can take 8 value. So 8 is purely integer, so that you can go for successive division method. Decimal to octal conversion, so that you can take 8 value and you can divide with 8. 8 ones are 8. So remainder is 0. So always you can go for bottom to top. 1, 0. 8 base 10, which is equals to, okay, 1, 0 base 8. That means was decimal 8 is equivalent to 1, 0 base 8. సో సింపుల్గా చెప్పాలంటే ఇందులో డెసిమల్లో ఏదైతే వాల్యూస్ 0 to 7 వరకు కన్సిడర్ చేస్తున్నామో సేమ్ వాల్యూస్ ఆక్టల్లో కూడా కన్సిడర్ చేస్తున్నాం 0 to 7 వరకు, రైట్? సో అంటే 0 to 7 ఈచ్ అండ్ ఎవ్రీ డిజిట్ హ్యావింగ్ సర్టెన్ వాల్యూ, ఆ వాల్యూ అనేది డెసిమల్లో అండ్ ఆక్టల్లో 0 to 7 వరకు సేమ్. సో 7 తర్వాత మనకి ఆక్టల్లో ఏంటి నెక్స్ట్ వచ్చే పొజిషన్ ఏంటి అని అంటే 1, 0 వస్తుంది, ఓకే. 1, 0 బేస్ 8 అంటే డెసిమల్లో ఏదైతే 8 వాల్యూ ఉంటుందో ఆ డెసిమల్ 8 వాల్యూని ఆక్టల్లో రిప్రజెంట్ చేయాల్సి వస్తే మనకి 1, 0 బేస్ 8 అనేది వస్తుంది. మనకి ఆక్టల్లో 0 to 7 వరకు లాస్ట్, అండ్ నెక్స్ట్ మనకి స్టార్ట్ అయ్యే పొజిషన్స్ ఎలా ఉంటాయంటే 1, 0, 1, 1, 1, 3 సిరీస్ అనేది మనకి అలా కంటిన్యూ అవుతుంది. సో మనకి ఇక్కడ డెసిమల్ లో ఏంటి 0 to 9, 0 is the minimum, 9 is the maximum. దీని తర్వాత ఏంటి మనకి నెంబర్ సిస్టమ్ ఎలా ఉంటుంది? సో 10, 11, 12, 13 అలా ఏదైతే ఫాలో అవుతుందో అలాగే సిమిలర్ గా 0 to 7 తర్వాత కూడా మనకు అలాగే ఫామ్ అవుతుంది. ఫర్ ఎగ్జాంపుల్ ఇక్కడ 8 కి మనం 1, 0 బేస్ 8 అని చెప్పేసి రిప్రజెంట్ చేసాం, రైట్? సిమిలర్ గా 9 ని కూడా మెన్షన్ చేయొచ్చు. ఇప్పుడు 9 అనేది డెసిమల్ లో ఉంది, దీన్ని మనం ఆక్టల్ లోకి కన్వర్ట్ చేయాలి. సో డెసిమల్ టు ఎనీ అదర్ బేస్ సిస్టమ్ కన్వర్షన్ అంటే ఏంటి మనకి? సో సక్సెసివ్ డివిజన్ ఆర్ సక్సెసివ్ మల్టిప్లికేషన్. ఇక్కడ మనకి ఇచ్చిన వాల్యూ ప్యూర్లీ ఇంటిజర్ కాబట్టి సక్సెసివ్ డివిజన్ ని ఫాలో అయితే సరిపోతుంది. సో 9 అండ్ యూ కెన్ డివైడ్ విత్ 8. సో 8 1s are 1 1 base 8. దట్ మీన్స్ వాట్, డెసిమల్లో 9 నెంబర్ని ఆక్టల్లో మనం 118తో రిప్రజెంట్ చేసేస్తాం, రైట్. ఇన్ ద సిమిలర్ వే 10 base 10ని, ఓకే 11 base 10ని, సో ఇలా అన్ని వాల్యూస్ని మనం 8లోకి కన్వర్ట్ చేయొచ్చు, రైట్. సో ఇది కన్వర్షన్ మెథడ్. కాకపోతే ఇక్కడ ఏంటంటే ఒక సిమిలారిటీ ఏంటంటే ఆక్టల్లో అండ్ డెసిమల్లో 0 to 7 వాల్యూకి బైనరీ నెంబర్స్ వచ్చేసి సేమ్గా ఉంటాయి. 0 to 7 వరకు డెసిమల్లో యాజ్ వెల్ యాజ్ ఆక్టల్లో ఏవైతే వాల్యూస్ ఉన్నాయో అవి సేమ్. ఓకే 7 అంటే డెసిమల్లో ఏ వాల్యూ ఉంటుందో ఆక్టల్లో కూడా అదే వాల్యూ ఉంటుంది. 6 అంటే డెసిమల్లో ఏదైతే వాల్యూ ఉంటుందో మనకి ఆక్టల్లో కూడా సేమ్ వాల్యూ ఉంటుంది. అంటే సేమ్ వాల్యూ అనేది ఎగ్జిస్ట్ అయినప్పుడు రిప్రజెంటేషన్ కూడా సేమ్ ఉంటుంది కదా. అంటే 3 అనే వాల్యూ తీసుకుందాం డెసిమల్లో, ఇక్కడ ఏదైతే వాల్యూ ఉంటుందో ఆక్టల్లో కూడా సేమ్ వాల్యూ, రైట్. సో అలాంటప్పుడు డెసిమల్లో ఏదైతే రిప్రజెంటేషన్ బైనరీ రిప్రజెంటేషన్ ఇస్తున్నామో సేమ్ రిప్రజెంటేషన్ ఆక్టల్లో కూడా యూజ్ చేయొచ్చు అనేది నా ఒపీనియన్. సో నౌ ఫస్ట్ ఐ విల్ టేక్ 0. ఇన్ ద ఫస్ట్ కేస్ ఐ విల్ టేక్ 0. దిస్ ఇస్ బైనరీ రిప్రజెంటేషన్ 0. ఫర్ ఆక్టల్ 0 I have to represent binary representation, that is 0. 0 means for example 0 value ni decimal loki convert చేద్దాం అనుకున్నాం. సో అప్పుడు ఏంటి 2 power 0. 2 power 0 means 1. That means 1 into 0 you will get 0, right. So that means 0 1. 0 is enough. Next I want to represent a binary equivalent for octal 1. That means what, I will take 1, right. So this 0 and for this 1. 1 means what is the decimal value of 1? For example you have a number representation like this is your decimal point and this is 2 power 1, 2 power 2 and this is 2 power minus 1 and 2 power minus 2, right. This is your representation. So now here the first, there is no fractional portion here, right. So direct integer. So that means this is first box. 0 means 2 power this is 0 and this is 1 and 2 power 2 and 2 power 3 like that, okay. So in the first place we have 0. That means that is positionally weighted with 2 power 0. Then you will 2 power 0 means what, 1. So this 1 into 0 you will get 0, right. Next you can take 1. Okay, that means for in first place you will take 1. After that you can apply positional weight for this. Then you will get 2 power 0 into 1. Then what you will get, 2 power 0 means what, 1. So 1 into 1 means what, 1. So that you will get 1, right. That means this is binary 1. So for this decimal value equals to 1. So decimal as well as octal both are same for 0 to 7. I will take 0 binary representation. Okay, and the next case 1 is the binary representation. For third case, okay, that is octal 2. So what is the binary equivalent? Just I will take, so for one binary bit that is not possible. So if you take only single binary bit, so you can't able to represent 2. So that's why we will go for 2 binary bits. 2 binary bits means we have 4 possibilities, right. That means 0 0 0 1 1 0 1 1. These are the 4 possibilities if you want to represent with the 2 binary bits, right. So first of all I will take this 0 0. 0 0 means what, so 0 0 that is 2 power 0. Okay, if you apply positional weight system, 2 power 0 and 2 power 1. So 0 into 2 power 1 plus 0 into 2 power 0 means obviously you will get 0 only. Next case 0 and 1. So for this 0 and 1, first 2 power 1 into 0 plus and 2 power 0 into 1. So this is completely 0 and this 2 power 0 means 1. So you will get 1 here. But our value is 2, whether in octal or decimal. 2 value is same. So we want to represent 2. Here I got only 1. Next I will move for this 1 0 position. In this 1 0 position, so first 2 power 1 into 1, okay, plus 2 power 0 into 0. So 0 into something means you will get 0 and 2 power 1 into 1 means 2. That means you can represent this 2 with 1 0, right. Now you will write here 1 0, clear. And next in the same way you have to represent binary equivalent for this octal number 3. Octal number 3 and decimal number 3 both are having same value, right? So and next we calculated 0 0 0 1 and 1 0 1 1. For 0 0 means 0, 0 1 means 1, 1 0 means okay. So here all these first positions are positionally weighted with 2 power 0, and for all these second positions are positional weighted with the 2 power 1, right? So already in previous case we calculated for all these three things, and now you can choose this 1 1 position. So 2 power 1 into 1 plus 2 power 0 into 1. Now so 2 power 1 into 1 means 2 plus 2 power 0 means 1, that 1 into 1 means 1, so you will get 3. That means, so you can represent this octal 3 or decimal 3 with binary equivalent 1 1, right? Now you can represent with 1 1, right? Now it is clear. Okay, so by taking these two binary bits, we can get a 0, and we can get 1, and we can get 2, and we can get 3. What about 4? That means so in order to represent this 4, so two binary bits are not sufficient, right? In the first situation, 0 and 1 you can represent with 0 and 1 binary bits, that is enough. When we move on to 2, we are unable to represent with single binary bits. That's why we can move on to two binary bits. With the help of two binary bits, we can able to represent 2 and 3, right? So for 4, whether it is octal or decimal, so in order to represent this 4, so two binary bits are not sufficient. In that situation, we have to move for 3 binary bits, right? So in that case, what happened? So for example, if you take 3 binary bits, so we have 8 possibilities, okay? 0 0 0 and 0 0 1, 0 1 0 and 0 1 1, and next 1 0 0, 1 0 1 and 1 1 0, 1 1 1. First 4 and next 4. Total 8 possibilities, right? If you take 3-bit combination, if you consider 3-bit combination, we can get around 8 possibilities, right? Out of 8 possibilities, which one can use to represent this 4, octal number 4? So that is important, right? So now you can check. So 0 0 means in first position we should consider as 2 power 0, in the second position we should consider as 2 power 1, and third position we should consider as 2 power 2. So 2 power 2 multiplied with 2, 2 power 1 multiplied with 0, 2 power 0 multiplied with 0, finally this will get 0. In the same way this will get 1, and same way this will get 2, and same way this will get 3. Now you can come to this 100. So first position is 2 power 1 2 power 2 into 1, and the remaining 2 are 2 power 1 into 0 plus 2 power 0 into 0. So 0 into something means this complete thing will become 0. And what about this one? So 2 power 2 into 1, that means we will get 4. That means, so in order to represent this octal 4, so we can use 1 0 0, right? 1 0 0, right? That is clear. Now, so here you can observe. So next 5. So if you want to represent a binary equivalent for this octal 5, so already this is 4, right? So you need to add incremental value 1, right? Then it will become 5. So this is 1 0 1 at the last position. Okay, this is 1 0 0. That means this is 2 power 3, 2 power 2 and 2 power 1, 2 power 0 position. So 2 power 1 is multiplied with 0, you will get 0. 2 power 0 multiplied with 0, you will get 0. 2 power 2, that means 4 multiplied with 1, you will get 4, right? Now you want to represent 5, that means you need to add, already this value become 4 and this value becomes 0, and if you add 1, you will get 5, right? So that means what? If you enable this first position, then you will get your the octal 5 equivalent value. Just I will make this one as 1. So then what happened is 2 power 0 into 1. 2 power 0 means what? 1. 1 into 1 means what? 1. Then you will get 5. Then octal 5 representation is what? 1 0. If you want to represent binary equivalent for this 6, okay, so just I will take 4 as it is, okay, and this time you can enable the second position and you can disable this first position. That means what? So I will take this one as 0 and this one as 1. Now what happened? 2 power 2 into 1 you will get 4, 2 power 1 into 1 you will get 2, 2 power 0 into 0 you will get 0, then it will become 6. That means what? In order to represent this octal 6 at decimal 6, okay, the binary equivalent representation is what? 110. And now you want 7. That means it's one incremental value. 6 plus 1, 7. Already you have 110. In the last position you can enable 1, then you will get 7. For example, here you will take 1. Okay, now what happened? Already this one is 4 plus 2, and 2 power 0 into 1 means you will get 1. 2 power 0 equals to 1, 1 into 1 equals 1, then you will get 7. So octal 7 or decimal 7 can be represented with triple 1 in binary format. These all are binary equivalents for octal digits 0 to 7. Just you can observe here, in order to represent binary equivalent for all octal digits, we can use maximum 3 bits, right? If you want to represent this 7, so we need maximum 3 bits. Final conclusion ఏంటంటే మనకి ఇందులో, సో ఆక్టల్లో ఉన్న 0 to 7 డిజిట్స్ ని రిప్రజెంట్ చేయడానికి మనకి మాక్సిమం 3 బైనరీ బిట్స్ అనేది యూజ్ అవుతాయి. 0 ని రిప్రజెంట్ చేయడానికి 1 బిట్ ఈజ్ ఎనఫ్, 1 ని రిప్రజెంట్ చేయడానికి 1 బిట్ ఈజ్ ఎనఫ్, 2 ని రిప్రజెంట్ చేయడానికి 2, 3 ని రిప్రజెంట్ చేయడానికి 2 బిట్స్, బట్ 4 to 7 వరకు రిప్రజెంట్ చేయడానికి మాక్సిమం 3 బిట్స్ అనేది రిక్వైర్డ్ అవుతాయి. ఇప్పుడు ఒకసారి ఇక్కడ అబ్జర్వ్ చేయండి. ఓకే, 3 పొజిషన్ లో, ఓకే, ఇక్కడ మనకి 2 బిట్స్ ఉన్నాయి కదా. ఓకే, వీ హ్యావ్ 2 బిట్స్, రైట్? So left most side, so you need to add one more bit, that is 0. Okay, one more bit 0. సో ఈ 0ని లెఫ్ట్ మోస్ట్ సైడ్ లో యాడ్ చేయడం వల్ల ఈ వాల్యూ ఏమైనా చేంజ్ అవుతుందో ఒకసారి చెక్ చేయండి. ఓకే, లాస్ట్ 0 యాడ్ చేస్తున్నాను. ఓకే, సో ఈ 0 యాడ్ చేయడం వల్ల ఈ 3 వాల్యూ ఏమైనా చేంజ్ అవుతుందా చెక్ చేయండి. 3ని రిప్రజెంట్ చేయడానికి మనం 1 అనేది యూజ్ చేసాం, లాస్ట్ లో 0 యాడ్ చేశాను. ఈ 0 యాడ్ చేయడం వల్ల ఏమైనా చేంజెస్ అనేది అక్కడ అవుతున్నాయి, అది ఒకసారి మీరు అబ్జర్వ్ చేయండి. సో 0 ఇక్కడ యాడ్ చేస్తున్నాం, ఏమవుతుంది? 2 power 2 into 0 అవుతుంది. 2 power 2 into 0 అంటే ఈ వాల్యూ అనేది మనకి ఎలాంటి చేంజ్ ఉండదు. అండ్ ఇన్ ద సేమ్ వే లెఫ్ట్ మోస్ట్ సైడ్ ఇక్కడ కూడా 0ని యాడ్ చేయండి, వాల్యూ ఏమైనా చేంజ్ అవుతుందా? నో చేంజ్. అండ్ సిమిలర్ గా ఫస్ట్ 2 డిజిట్స్ కూడా లెఫ్ట్ మోస్ట్ సైడ్ 2 zeros యాడ్ చేయండి. ఓకే, ద సేమ్ వే దిస్ వన్ ఆల్సో. ఇప్పుడు వాల్యూస్ ఏమైనా చేంజ్ అవుతున్నాయా? లేదు. అంటే ఫైనల్ గా మనం ఏం కన్క్లూడ్ చేయొచ్చు ఇక్కడ? సో in order to represent octal digits in binary format, we required maximum 3 bits, 3 binary bits. That is the conclusion, right? సో ఆక్టల్ డిజిట్స్ ని బైనరీలో రిప్రజెంట్ చేయడానికి మనకి మాక్సిమం 3 బైనరీ బిట్స్ అనేది రిక్వైర్డ్ అవుతాయి. సో దాన్ని లాజికల్ గా ఎలా రిప్రజెంట్ చేస్తారంటే, బేస్ r equals to 8. ఓకే, దిస్ ఈస్ యువర్ ఆక్టల్ representation. Octal, when comes to binary number system, r equals to 2. So this 8 can be represented 2 power 3, and here binary can be represented with 2 power 1. Now you can check here. So here the power equals to 3. Okay, and here the power equals to 1. That means each octal digit required 3 binary bits. That is the logical representation. 3 bits are required in its binary representation of octal number, right? So that is the logic. For example, if you take r equals to 16, okay, otherwise and here r equals to 2. Okay, now this can be written as 2 power 4, and this can be written as 2 power 1. Now here the power equals to 4, and here the power equals to 1. That means each hexadecimal digit will require 4 binary bits in its binary representation, right? For example, if I am taking r equals to 32, okay, 32 base system, and here r equals to 2. Okay, now so this can be represented as 2 power 5, and this can be represented as 2 power 1. And now just I want to represent this base 32 system in its binary equivalent. Okay, in that situation each base 32 digit will require maximum 5 bits in its representation. This is logical interpretation. Okay, this complete already we discussed the theoretical aspect how we assign 3 bits for octal. Power will indicate maximum number of bits in its binary equivalent. So I will conclude with one statement. So replace each octal digit by its 3-bit binary equivalent. Okay, so whatever the octal digit we have seen. Okay, so for each octal digit we can replace with 3 binary bits in its binary representation, right? So that is the final conclusion. Wherever octal digit is there, if you want to convert it into binary format, just you can replace with 3 binary bits. That is enough. I mentioned, right? So for 0 000, for 1 001, for 2 010, for 3 011, for 4 100, for 5 101, for 6 110, for 7 111. So you have to remember all these. And next, this is your example 542.13 base 8 system. So the given system is octal system, so you need to convert it into binary format. So octal to binary conversion in this case. Okay, so we have to follow two methods, okay, integer and as well as fractional conversion. So in this integer method, so you have to move from least significant digit to most significant digit. That is very important, right? So when you are converting from octal to binary representation, first you can focus on integer, after that you can focus on fractional portion. While converting integer octal to binary format, so you can move from least significant digit to most significant digit. When you concentrate on fractional portion, you can move from most significant digit to least significant digit. That is very important, right? So here I am expanding 542.13 base 8 system. First you can start with this least significant digit. After that you can move from leftmost side, and after that you can move from most significant digit. That means right to left. Okay, first you can take 2 and you can replace with its binary equivalent, that is 0 1 0, and next you can go for 4. So this octal 4 having its binary equivalent, that is 1 0 0. So you can replace this 4 with the binary equivalent 1 0 0. And next you can take 5. This is most significant digit. So for 5 octal digit, so the binary equivalent is 101 from this table, right? Similarly, you can convert a fractional portion of octal number to binary representation. So first you can move from most significant digit to least significant digit. That means left to right. Okay, left to right movement for fractional conversion. So that is for 1 its binary equivalent 001, for 3 its binary equivalent is 011. So this is your entire binary conversion. That 542.13 base 8 equals to 1011000010.001 base 2. This is octal to binary conversion. We will look into one more example, that is 725.63 base 8 system. So you need to convert it into binary equivalent. Same pattern. First you have to convert 5, and after that 2, and after that 7. That means least significant digit to most significant digit movement, that is right to left movement. And whereas in fractional portion, left to right movement, that is most significant digit to least significant digit movement. Okay, so just you can replace this octal digit with its binary 3-bit binary equivalent representation. Then you can combine all the binary bits, then you will get your exact binary equivalent representation for a given octal number system. Then next we can move for binary to octal conversion, right? So binary to octal conversion, we have 2 steps. First, divide the binary number into 3 bits each. So whatever the binary equivalent number is there, so that number you can divide into 3 bits each. Okay, that is step 1. Okay, next step 2, replace each 3 bits group by its octal equivalent, otherwise octal digit. Okay, replace each 3 bits group by its octal digit or octal equivalent, right? So this is your example, that is 10110111.11010. This is your binary number. So the given number is binary number. So the required number is base 8 number, that is octal number system, right? So what you have to do, first you can divide all the 3 bits into one group. After that you can assign octal equivalent. Then conversion is over. binary to octal conversion is over. In previous case also we can move from a least significant digit to most significant digit for integer, and for fractional portion conversion we can move from most significant digit to least significant bit. That means integer means we can move from right to left, for fractional portion means we can move from left to right. Here also same thing. If you want to divide 3 bits each, so you can move from a least significant bit to most significant bit for integer conversion. When you go for fractional conversion, yes, you can move from most significant bit to least significant bit. That means left to right. Okay, so just you can observe here. Here I can move from least significant bit to most significant bit for division of 3 bits, right? So now here 110 is one group, and 101 is another group, and next 110 is another group, and the last bit is 1. So, and the last group having only one bit. So in that situation, so our step 1 is what? Divide the binary number into 3 bits each. But in the last case we have only one bit. In that case you have to add 2 more zeros in its leftmost position. Okay, in that case you have to add 2 more zeros in its leftmost position. By adding these two zeros, this adding 2 zeros is called as padding method. So we will discuss in later stage. Okay, so these 2 zeros, by adding these 2 zeros, the integer value cannot be changed. That you have to remember. By adding these 2 zeros in its leftmost position, the integer value cannot be changed. So that's why I can add 2 zeros in its leftmost position. Now each group having 3 bits. Now you can replace its octal equivalent. Then binary to octal conversion is over. So in this case what happened? 011 means 3, 101 means 5, 011 means 3, 001 means 1. This 1353 is the octal equivalent for a given binary 3-bit segments, right? Next we can move for this fractional conversion. In this case what? So we can move from most significant bit to least significant bit. That means left to right movement, right? So from left to right you can divide each 3 bits as a group, right? So first 110 is one group, 10 is the another group. But in the last group we have only 2 bits, but we need, according to our conversion steps, so we need 3 bits, right? But we have only 2 bits. In that case you need to add one more 0 in its rightmost position for a fractional number. Okay, in that case you need to add one more 0 in its rightmost position. Rightmost position means least significant bit side. Okay, so you can add 1 0 at rightmost position for fractional number. By adding that 0, okay, the fractional value cannot be changed. That's why I'm adding 0 at rightmost position of fractional number. So now each segment having 3 bits. So the 3 bits can be replaced with its octal equivalent, right? So now 110 means the octal equivalent is 6, and 100 means its octal equivalent is 4. Now can combine these two, then you will get 1353.64 base 8, right? This is your binary to octal conversion. So I will take one more example. So the given binary number do not have its fractional portion, so only we have integer binary number, right? Integer binary number. For a division of each 3 bits, we have to move from least significant bit to most significant bit. That means right to left, right? Here this one is your least significant bit, this is your least significant bit, and this is your most significant bit. Okay, now I can mention here. So 1 1 1, 4 ones, 0 1 1 0 0. So you can start from rightmost bit. Okay, that means the least significant bit. Here LSB. Okay, otherwise rightmost bit. Okay, rightmost. Now you can go from rightmost bit to leftmost bit. Then you can divide with 3 bits. Okay, this you can divide here. Okay, and next you can divide here. Okay, so each segment having 3 bits, each group having 3 bits. Now you can assign with its octal equivalent. Then what you will get? So 100 means what? That is 4. Okay, and 101 means what? 5, and 111 means what? 7. 111011000 base 2, which is equals to 754754 base 8. This is your octal equivalent. So this is your octal to binary conversion and binary to octal conversion. In the next session, so we will cover hexadecimal to binary conversion and binary to hexadecimal conversion. Okay, thank you.